Hi, welcome to another lecture on linear algebra. Today, the most important topic we are going to talk about is the culture shocks that the student feel when they take this class. At the beginning of the semester, we said most engineering students take 6 courses in mathematics: calculus 1, 2, 3, linear algebra, differential equations, and statistics. And somehow linear algebra stands out from the crowd by having many different features to it, and occasionally some students feel a little bit lost in the course. I tried to give a heads up today to make sure that we resolve these issues and the students wouldn't have that block that sometimes they feel in this class. Let's go ahead and see what the topic is about today. In addition, we are going to talk about some standard linear algebra things as well, easier topics for today. So topic number 1, we are going to talk about linear versus nonlinear equations. So the title of linear algebra, the word linear, what does that mean, and how do you distinguish linear from nonlinear? Then item number 2, the big item for today is, when you come to solving systems of linear equations, you are going to have these culture shock issues. We are going to talk about the issue of large data sets, infinite solution sets, and empty sets. See how we are going to handle these items. Then we go back to some standard issue topics. Certain nonlinear systems can be transformed by substitution to a linear system, and we are going to talk about that. Okay, let's go start with the item number 1, linear versus nonlinear equation. So let's write some examples. Linear examples, we have seen plenty of these things. So simplest example, 2x plus 3y is equal to 5. Or in general, say ax plus by is equal to c. So you see the variables occur as themselves. Nothing else is done to them other than multiplying by a constant in adding and subtracting and making equal to some constant. The issue could be, how many variables you might have here. So I can have as many as I want. So say 5x plus 6y plus 11z equal to say 12. We saw this type of equation when we talked about equation of a line, and here is a general form of that type of an equation. We can go and include more and more variables. At some point, using letters of alphabet is not going to be a smart thing to do. We have to use subscripts. So we use some generic letter for our variable and subscript it with say x1, x2, x3, as many of these things as you might have. So we have a fixed number of them in any given problem. So the last one of these things, perhaps x sub n, perhaps it can be x sub 1000 or maybe 7 or whatever it is. And then we can have coefficients for these things. Those coefficients, we write them with the subscripts as well. A1, A2, A3, and so on we go until say AN. And right hand side would be some constant. Let's just write it as a B. So this is going to be the general linear equation in n variables. What's a nonlinear one? The issue is rather subtle as to what is linear and what is nonlinear. I'm not going to get into fine details of that today, but as a general rule of thumb, we kind of say that if you see an equation which has powers in it, let's say x to the power of 2, or radicals in it, or exponentials in it, or any other function, cosine of x, and so on, or fractions in it, these will be nonlinear. So, but there's a tiny fine print next to these things. Sometimes linear equations masquerade as non-linear, so sometimes you have to go simplify and clean up, and then at the end you see that your equation was actually linear, just made itself look like these. But that those cases are rather rare. So if you have an equation like x squared minus y cubed equal to 5, well, that looks mightily different from this one. And one good way to see the difference, just go ahead and experiment with these things. Let's go ahead and take a look at some software we have. So for 2D dimension, most excellent software is Desmos. So let's go ahead and do a linear one. Say y, this is what you did in elementary school. Y equal to 2x plus 1, you get a linear graph. It's kind of a featureless thing. It goes at a certain rate, and any portion of it is a copy of all of it, and so on. But if you experiment further, like x squared minus say y cubed say equals to 5, let's clean this one out. Of course, what you see is that you see a curve. There's a curvature that changes, typically some sort of bending here and there. These are indication that you are dealing with a nonlinear equation. Any kind of a curvature, holes, asymptotes, and so on. These are telltale signs of a non-linear equation. If you want to experiment in 3D, perhaps the best free software here is this one, CalcPlot 3D, thanks to Paul Seeberger. Here's a simple equation: z is equal to 2x minus y plus 1. You can of course play with this thing and see that this is also a featureless shape. Whatever direction you go, it's just duplicating itself and going, as opposed to what? Well, let's just erase that and bring out the standard picture of this website. Well, you see plenty of curves and ups and downs here, and that's indication that you're dealing with a nonlinear equation. So in 2 and 3 dimension, we have this software. We can look at what the graph looks like and make a judgment on that. As a matter of algebra, if you simplify it into this shape or this shape, then you have a linear equation in general in n variables. That's going to be your general linear equation. Everything else, which is a much bigger bag of all sorts of equations, will be considered nonlinear. Okay, we are going to leave that issue alone. Digging deeper is going to require some material that's going to be beyond the scope of this class. Let's go to the biggest issue for today. The issue of culture shocks in linear algebra. That's probably biggest item at the beginning of a semester. So we say that once you get into this class, one of the things that you see is the problems have lots of numbers in them. So you're dealing with large data sets. This is quite common. It's not so unusual for a student to be asked to, for example, solve this system of equation. So you see a system of 6 variables, 6 equations. When you look at that, immediately you're struck by something. There are like 42 numbers here. Well, you're just coming from Calculus 1, and it is quite safe to say you never started a Calculus 1 problem with 40 numbers to begin with. I mean, they typically have 1, 2, 3 maybe at most, and at the end you're just finding 1 or 2 numbers. But in linear algebra, we have to settle for the situation that there are many numbers to begin with. Even the smaller problems, do have quite a few numbers in them. There is nothing to do to avoid that. So what does that mean? First of all, well, writing this is going to be a task all by itself. As a challenge to write 42 numbers. Next, well, how do you solve this thing? Solving this is going to require about 200 arithmetic operations. That's plenty. writing the solution itself is a task. So there are quite a few challenges. First of all, we want to say that, well, just to relieve your mind, we are going to introduce you to some software to take some of the pain away. But the fact that you are going to be dealing with large systems or what appears to be large to you, that is part of the game. In fact, as you go become an engineer, if you do any major calculations, you're going to come across systems that could be thousands of lines long. It's not unusual to come across that situation at all. So let's accept that and not build a mental block or something, go to some corner and sulk and say I'm not going to play and such. It can be handled. That's how it is, and you want to recognize that going in, that there is a challenge to overcome. Okay, issue number 2, infinite solution sets. That's another culture shock you come into. When you have calculus 1, you solve a problem, for example, find the maximum point, minimum point, and stuff like that. At the end, you have one x, maybe an x and a y, and that's about it. But here, it's quite common that what we are looking for itself has infinitely many pieces. It's not just a single number. So let me write that here. So the issue of infinite solution sets, that is something to get along with. Let's make the problem very simple. Suppose I ask you to solve x plus y equals to 10. Okay, the equation itself looks like something from almost elementary school, but you have an uneasy feeling if you can express it or not, which is, well, I can give you lots of answers. I can say x was 1, y was 9, or I can say x was 2, y was 8. I don't have to stick to whole numbers. This can be 3.5, and this can be 6.5. It can be negative, it can be -5 and 15, and so on. I have many choices. What do you mean by solution? Well, this is exactly what we mean by solution. That whole table you just created in your mind, that is the solution. So our solution is a crowded set. It's not just one number. So yes, back in whenever we solve some equation, there comes 1x proudly exhibiting itself or something. But now situation is different. Well, handling an infinite table and giving it to somebody is not a practical thing. We have to find an alternative, either a formula that goes with this thing or a picture that goes with this thing. Of course, a picture is the easiest. Picture you have seen back in beginning of middle school as well. So you draw this. What do you mean by this thing? It means every one of these points on this line. So this is the equation of this graph of the x plus y equals to 10. That graph has infinitely many points on it. Who are these points? Those points, each of them is one of these pairs of numbers. So what is important to realize is that that line is the solution. Okay, so the solution hasn't to be just x equal to 5 and you're done. An entire line, an entire table could be a solution. Well, in linear algebra, neither of these are going to be practical ways of dealing with the bigger systems. What we are going to do is to bring in bigger guns, which is parametric solutions. Parametric solutions means, well, we are going to choose one of these variables as our parameter, and the other one is going to be decided in terms of that parameter. Meaning, if I give you the location, the value of y, can you figure out what the x is going to be for me? In this problem is going to be quite easy. If y, I tell you y is t, well, who is going to be x? X is left with 10 minus t, because the sum has to be 10. Well, next issue comes up is the style in linear algebra. We pack this as a vector. So pack this thing as a vector. Then we separate if you wish, separating oil and water. This is a 10, there's nothing here, so this is a 10 and a 0, and the other piece is minus t and a t. We make this thing look even nicer than that. X and y is 10, 0, factor a t out of this, minus 1, 1. Well, if you remember from previous lectures, this was some kind of a starting point. For example, we might choose this as our starting point, and then minus 1, 1 is a direction vector. This is a direction vector, like in this case going this way. So that's how you take steps. You start at this point like here, and then you take steps, copies of this vector, and go up and down this street if you wish. That constitutes your solution. Okay, so that's the issue of infinite solution set. Sometimes this becomes a bit more crowded than that. So let's do two things. One is the issue of who gets to be the parameter and such. Let's talk about that. And then solution sets that are even more crowded than this. Well, here I said let y to be t. You say, well, why not choose x to be t? Well, that's perfectly fine. You could have chosen y, you could have chosen x. We are going to make a kind of a tiebreaker here, how to go about this thing so that everybody comes up with the same solution. We start from the very last variable. If it can be a parameter, we declare it as such, and then we go backward and decide on the fate of those. Okay, so when an equation is written, we start from the very last variable. If it can be a parameter, we declare it as a parameter, and then we move on. In your textbook, most often the parameters are shown by t and s, sometimes some other letters as well. So long as the letter that you choose here is different from all the letters you had so far, you are fine. But almost all problems, they either have a t or an s in them. So if you wanted, you could have said x is equal to, say, s, and then y is equal to 10 minus s, and then the solution of that equation also would have been written as, now 0 and 10, you do exactly the same thing as before, and s, and 1 and minus 1. The one that we go with is this, because we choose y to go as our first chosen variable to become a parameter. What if our equation was more crowded? So suppose I say x plus y plus z is equal to 10. Okay, so this equation, x plus y equal to 10, is like me telling you I have $10 in two pockets. Tell me how much money is in each pocket, which you are going to object. Now, how can I tell how much is in each one or the other? It could be lots of choices. And again, that's our culture shock. Yes, that's the situation we are dealing with. Now we are making it worse. We're saying I have three pockets. The sum total of all the money in all of them is 10. Tell me how much is in each. And you are going to say, well, tell me how much money you have in two of the pockets, and then I'm going to tell you how much is left in the third pocket. That's what we are doing here. So in this case, we start from the very last one, z. That has to be a parameter. Okay, that still doesn't determine what y is going to be. Y has to be some other parameter. So by now I have told you how much are in two of the pockets, so we are going to know what is in the third pocket. So x becomes 10 minus s minus t, and then x, y, z, just like the previous equation, we have our constants 10, 0, 0. Maybe I write this thing, and then from now on we are going to let me write it all up, and then separate it in several steps for you. So this was 10 minus s minus t. This is s but no t's. This is no s's but a t. So we are going to separate into three groups: 10, 0, 0, That is the, let's color it, and then color the next one. So I'm going to color that here. So I take the s out. What is left? Minus 1 is here, and now 1 is here, so let me write it minus 1, 1 and 0. And finally, how about t? You go ahead and do that before I write it and come back. Is that right? So our idea was that you go ahead and do these things instead of waiting for me to do it. So you take a look at that, and so t, let's color it, say green. So we have what do we have? It's minus 1, this is 0, and this is 1. What does this look like? Well, you remember that was the equation of a plane at the beginning of semester, and then we had the equation of a plane written by two direction vector. In that explanation, this was some sort of a starting point. There was a point on the plane. This was one direction vector, so some direction vector, maybe we called it u or something, and then this was another direction vector. Let me remind you what the issue was. So this was in 3 dimensions because we have x, y, and z. So we have some point, some starting point. It could be anywhere in space. Let me just, of course this is on the x-axis, but let me just choose some point. So this is some starting point r0, and then we have some vector, maybe we call it u, another vector we call it v. So I have a vector u and a vector v. S times u means you are allowed to take any multiple of u, like 2u's, 3u's, or any multiple of u, including negative and such. T times v means you are allowed to take any multiple of v, and you are adding these things means you're going to r0, so this was our r0, and say you add 1u and to 1v. Well, by that time you are going to be in this location. If you take 2u's and add 1v, you will be in this location. If you take 2v and 1u, you will be in this location, and so on. So what does this create for you? This is going to be some sort of a tiling work in space. Essentially it's a plane. This is a plane, and this, you remember, this was the general equation of a plane. So equations that have an infinite solution set, and they represent curves and surfaces for us, and most often in linear algebra these curves and surfaces, well, this becomes a straight line here, and this becomes a plane here. In these two examples we could actually look at them, have a feel for them. But as the number of variables increases, you go to 4 dimensions, 5 dimensions, such, unfortunately we lose our ability to see in those dimensions. We are going to rely on algebra. Algebra is going to be our kind of a guide dog in higher dimensions. It's going to let us know what's happening there, even though we cannot see it and we are blind to it. Okay, so we talked about large data sets, which is lots of numbers comes on into standard linear algebra problems. It's quite common to end up with infinite solution sets. We looked at the simplest example of these things, and alternatives to an empty solution set. So we gave a very simplistic example of empty solution sets in the previous lecture. Empty solution set. Here's a very simple example. If I tell you solve x minus y is equal to 1, and say 2x minus 2y is equal to 5, what would you say? We say, well, if x minus y is equal to 1, if you double on the left, you have to get 2. You cannot get 5. What's happening here? Well, these are, if you graph each of them, it's a equation of a line that is also a line with the same slope, and they end up being parallel to each other. So if you draw this thing, for example, you get a line like this, you draw this one, and you get another line, perhaps here, that's parallel to the first one. Since they do not intersect, there's no x and y that satisfy these things. We call these things inconsistent. Okay, so in high school, elementary school and such, you come across this thing, it says, okay, no solution, or it does not exist, and one thing or another, and essentially you brush this to the side and you move away. Well, then you grow up. Then you grow up and you come to linear algebra. You go to the next more advanced version of this class, and then there they are going to insist that, okay, our equations don't have a solution, but what's the best that we can do? So we kind of approximate real life here. It's like, okay, we don't have a perfect solution, but what is the best we can do? We actually come to this issue in all of your experimental labs. If you go to a lab, the most basic labs, it could be circuit class or something, and you're just dealing with resistance and currents and voltages and such. So for example, suppose you are studying Ohm's law, which says voltage is equal to resistance times the current. So you go ahead and measure the current, you go ahead and measure the voltage, you draw the numbers that you have on the coordinate system, and say, suppose this is I and this is R, and you expect to get you expect your data to sit on a line, and the slope of that line is going to be R. Okay, so just like when you say y is equal to mx, here our v is equal to ri. Okay, well, when you go to the lab, all of a sudden you see, and that's the end of the rosy scenarios you have been looking at in math classes. The points don't line up the way you want them to line up, so this could fall short. This one could go higher up, this one could come down, the other two could go higher up, and so on. So there is not a line that goes through all of these data points that you have. So if you want to take this point of view, you're going to come out of the lab and write on your report no solution or inconsistent, or something like that, and your lab instructor is going to look at you with strange eye. What do you mean no solution? You were just playing with that voltage and that current, and there was a resistance there. I'm asking you to tell me the resistance in that piece that you had there. You cannot say it doesn't exist. You were just looking at it. So what is meant over there is that you want to make a compromise. You have overshoots, undershoots, and such. You want to go after a line that minimizes this kind of errors that you have. So you talk about these deviations, and then you come up with a way of assigning the best fit to data. So the issue of the best fit or curve fitting this arises when your equation doesn't have a solution, and then you're still trying to find the best you can do. Okay, that is a topic for the end of the semester. We typically don't get to that topic. It's going to be next linear algebra class, and you're definitely going to come across this thing in your lab classes, in your experimental classes, and also in your statistics class. But that falls under linear algebra really. So you're going to come across something called least square method, where the idea would be to measure these errors, square them, and add them up, and adjust the line such that deviations become as small as possible, and you say, okay, this is my best compromise in this situation. Okay, so alternative to an empty solution set, Right now we still say inconsistent or doesn't exist, but be prepared for something more elaborate than that. Uh, let me go ahead and just do one more a bit more serious example of this case. This is the one that gives the student most challenge here, which is, well, how do you go about creating your solution sets in that case? So let's do a problem on that one, infinite solution sets. Suppose the question is, solve the following: a minus b, or a minus 2b, and then plus d is equal to 2, minus a plus b minus c minus 3d is equal to 1. So this is an example of infinite solution sets. And the issue of dealing with the parameters and designating your final answer as to, well, is it a line, or is it a plane, or is it something else? So we have these progression of ideas. Well, you start with the point, and then you go to a line, and then you go to a plane, and higher than that, something else called a hyperplane, just more crowded version of a plane. And then sometimes you're asked, well, which one is it that you found? Here we are going to learn about elimination in the upcoming lectures, but let's do a preview of that. First equation, well, first equation just good as it is. I go ahead and eliminate, so we are going to hear this word quite often, eliminate b from the second equation. How do I do that? Simple, just add the two, and a is going to go away. So I'm going to end up with, when I add these two, I get a minus b, and then minus c, and then when I add these two, I get minus 2d, and 2 and 1, I get a 3. Okay, this sort of like this equation that we had here. So the way we handle this thing, we start from the last one. We say, well, let's call that a parameter. So I call, for example, d to be my, say, s or whatever. C, still a parameter, so it's going to be t. And then b is going to be determined from these things, so it's going to be minus 3. So if you take this thing and take the b to this side, I'll get b is equal to, take 3 to this side, minus 3 minus c minus 2d. Is that right? So b becomes minus 3, c became t itself, this c is t, d was labeled as s, so it's minus 2 s. And then we go ahead and find out what a is going to be. So whatever I have here, I put in this first equation. So somehow I have over there, I go and solve it as it is. It becomes 2 plus 2b minus d. So I write 2. My b is this, plus 2 times minus 3 minus t minus 2s. And then that's my 2b, and then I have minus d again, which is minus s. So I clean up, this becomes 2 minus 6 minus 2t minus what's that, minus 4s minus another s. So cleaning up, I get 2a is equal to minus 4. Is that right? And then how many t's do I have? It's just minus 2t. How many s's do I have? Looks like I have minus 5s. Okay, we pack this thing as a vector, a, b, c, d. First of all, it tells us we are in 4 dimensions. We have a bunch of fixed numbers. Let's list them first. Minus 4, minus 3, this is 0, this is 0, and then we collect the t's, factor it out, and say this is minus 2, minus 1, this is 1, this is 0. I also have a parameter s, and the numbers here minus 5, minus 2, and a 0, and a 1. So this is the solution set. The solution set infinitely many points on it. What kind of a creature is this thing? Well, let's go ahead, take a look at what does it look compared to what we had. I have two vectors or two parameters. That indicates this is a two-dimensional thing. What we have here is a two-dimensional thing. Two-dimensional means like a plane. So it's a plane, but can I draw a graph for it? Unfortunately not, because it's sitting in a four-dimensional world here. So I have two direction vectors, two parameters. They are sitting in 4 dimensions. So this is a plane, or a two-dimensional plane, if you want to call it. A plane in, how do we talk about a four-dimensional world? Here's a funny looking R with a 4 on top of it, meaning 1, 2, 3, 4. We are in 4 dimensions. That is what is done for this problem. We are going to come across much more elaborate version of these problems later on. In that case, we are going to help you with a software to go through the problem quickly. Okay, as a last item for today, we said we are going to bring up some side issue, not very significant here, is nonlinear systems that can be transformed to a linear system. So this is kind of a bit of algebra example from college algebra. And here's what is meant by that. Here's a problem in your textbook. Solve the following. Solve minus 2 to the power of a plus 2 times 3 to the power of b is equal to 1, and 3 times 2 to the power of a minus 4 times 3 to the power of b is equal to 1. The intention of this problem is to say that if you forget for a moment that there are some nonlinear things here, if you kind of hide this thing in a box and the same box here, if you hide this one in some box, hide this one in some box, then you can think about this thing as a linear equation. Meaning what? Meaning if you do a substitution, we do a substitution. So, okay, the yellow stuff, let's call it A. The blue stuff, let's call it B, so that we remember what it is. Then the equation looks like minus A plus 2B is equal to 1, and 3A minus 4B equals to 1. Okay, so here my equation looks non-linear. I do a substitution, I end up with linear. Well, linear we know how to solve. Once you do that, you get your A, you get some number, B, I leave that to you. B, you find some number. Well, then how do I find my little a and my little b? Well, this a, if I had 2 to the power of a and I found out what a is, say a was 5, 10 or whatever it is, how do I find little a? Obviously I take a logarithm. A logarithm of 2 is equal to logarithm of a, so a becomes logarithm of a over logarithm of 2, which if you remember from your pre-calculus, that by change of base formula, there's also logarithm of a in base 2, and all of these things will be equal to each other. So you find your a here, and then logarithm of that number divided by logarithm of 2 will be your answer for a, and same story for b. Of course, it's going to be logarithm of b divided by logarithm of 3. So you find it, and you give an explicit answer in this case. So these are the problems that with intelligent substitution become linear, and once they are linear, well, you handle it the way we have done in this class, and then at the end you do a back substitution again, and then so you from here you have to go back to what the little a is. Okay, so we covered we are here. We covered this topic as well, and we are ready for the next lecture where we are going to handle problems with more elements to it. Okay, until next lecture, good luck and God bless.